Hello everyone and welcome back to video lecture series on computer architecture. My name is Dr. Prashant Bachana. So in the today's video lecture, I'm going to cover these topics, that is instruction set architecture, addressing modes, and the different types of assembly language instructions. So we'll see it one by one. So first we will discuss about the instruction set architecture, that we will see what is an ISI. So the instruction set architecture is a part of the computer architecture related to programming, including the set of instructions that the computer can perform. So in the computer architecture, when designing in computer architecture, ISA defines the architecture, and in which all the addressing modes instructions are defined. And there's a term called as interface here that acts as an interface between the computer and the hardware. So this is about the instruction set architecture. Then what is the role of computing? That is the translation, that is converting the high level programming languages into the machine level language. So the instruction set architecture consists of the translation, that is the compiler, which will convert the high level the programs written in the high level language to the machine readable instructions. Then the performance and the efficiency, that is this defines how effectively a processor uses its capabilities, including influencing both the speed and the power consumption. Then the instruction set also defines the compatibility between the software for specific operations that can be performed on the hardware. So these are the key components of an instruction set architecture, that is instructions. So a program is written with the help of the instruction. The actual commands executed by the CPU are called as instructions, such as arithmetic operations, data movement instructions, and control flow instructions. Then the next part of an instruction set architecture is the registers. So in a computer, we know all the information executed, all the operations executed by the CPU is done with the help of the registers only. And we have also seen the types of registers, that is special purpose registers and the general purpose registers available. Then the registers are like small fast storage locations directly within the CPU, which are used for executing the instructions. The next type of the next part of the next component of the instruction set architecture is the data types. That is, what are the different types of the data types available for the hardware. That is, it defines the types and the sizes of the data that the hardware can handle directly. For example, the integers, floating point numbers. Then the next part of the instruction set architecture is the addressing mode. So addressing modes are the way in which the data is defined in a program. So that we call it as addressing mode. So in which we will there are different types are there, again we'll see in the coming part of the video. So these are the methods by which the instructions identify the location of an operand, that is an input data of an operation. So what kind of data we are mentioning, whether it is a direct data or immediate data or any other kind of data. So the addressing modes basically defines like how you are defining the data in a program, assembly language program. So this figure shows the interaction between the software and the hardware with the help of an instruction set architecture. As you can see here, this is the high level control here, and so this part is called as the embedded computer hardware, and this part is the software. So with the help of the instruction set architecture, both the things are interfaced here. As you can see the software here, Wi-Fi, USB, player, sensor, server, remote control, all these things are available in the Linux. And as you can see here in the camera and other things, and there is an like some simulators are there, so which have been used for the simulation. So this diagram shows then basic example of and how instruction is executed in a executed by the processor. So the instruction is basically executed in the three steps, that is fetch, decode, and the execute. So in between, it will take the address. So the first part of an instruction, that is The task of an instruction set architecture is to execute the instruction. That execution happens in this step. So the first, the instructions will be fetched from the memory, then the decoder will decode it, and decoding in the sense what type of operation to be performed. So whether it is an addition operation or subtraction operation or the division operation. So once the instruction is fetched, then the decoder will decode it, that what operation to be performed. So once it is decoded, then it will read the address, then it will be executed. So basically, processor execute the instructions in the three steps, that is fetch, decode, execute. So the foundation of any system design, that is the ISA, shapes the core capabilities of any computing system. It also influences the design performance of both the hardware and the software. So what is the impact of the software development? That is the first, and this one is the programming model. That is ISA defines the programming model for the developers, influencing how software is written and optimized for the performance. The second thing that it will take care is the optimization. That is, specific ISAs allows software to developer to leverage the hardware features like single instruction, single execution, and single instruction multiple data. That is SIMD. So that operations enhancing the efficiency of a particular application. That is, it is a use single instruction then multiple data. So in a single instruction we can mention multiple data. So, and which are also used for these like particular applications like graphical processing, scientific computations. Then the ISA will take care of the portability versus the optimizations. So while the softwares can be written in the high level language, but the programs, the computer understands only the machine language. So that portability will be taken care by designing the instruction set architecture efficiently. Then optimization performance are required. You need the help of the softwares to take advantage of the ISA features. Then what is the impact of the hardware design? So this figure shows an example of the how processor implementation is done. That is, a choice of an instruction set architecture directly affects the complexity of the processor. For example, the RISC instruction, that is reduced instruction set computing, leads to the simpler design, whereas the CISC is complex. So there are basically two types of the architecture here: CISC and the RISC. That is, CISC stands for complex instruction set computing computer, and RISC is reduced instruction set computing. So as the name itself indicating, RISC is simpler, CISC is complex. So this is how the instruction, when we are designing an instruction set architecture, we have to see whether we are going like based on the application, whether we are designing a RISC architecture or the CISC architecture. So the complex, in the complex instruction set computing, it is little bit complex because it is having only the instructions will be complex here, whereas in the RISC it is having fewer instructions, so that it is simple to execute. Then once we design this, in the key characteristics of the ISA is the addressing modes. That is, as we have already seen, the addressing modes are the different types in which we can define the data. That is, there are different types of addressing modes are there. We'll see it one by one. That is immediate addressing mode, direct, indirect, and index based addressing mode. So in the immediate addressing mode, the directed data will be mentioned. The direct data will be mentioned in the instruction, whereas direct addressing mode, the operand is directly stated in the instruction. Whereas in the indirect addressing mode, the address of the operand is specified directly via with the help of a memory, or with the help of a memory or location. So as we see the differences of, between the immediate, direct, and indirect, in the index and based um, addressing mode, the combination of both address as well as the index are used in the in the data structure. So in the immediate addressing mode, the direct value will be mentioned. Direct addressing mode, it will mention it in the instruction, and then in the indirection, either will mention in the register or memory location, and in the indexed in the base is a combination of address and the indexed addressing mode. So here we will also look into the sizes of the operands here. Let us say there is like different types of, means like when we are mentioning the operands, Operands, the size of operands may be 8-bit, 16-bit, 32-bit, or 64-bit based on the processor. If it is whether it is an 8-bit processor or 16-bit processor, the instruction there will be variation in the sizes of these operands. Then the impact on the performance, obviously it will have an impact on the performance. That is that the larger operands might enhance the performance of the, let us say if it is a 32-bit size operand, then that processor will be high compared to the 8-bit operand size processor. Then the instruction set also supports the types of instructions that is available, that is arithmetic and logical operations, like addition, subtraction, multiplication, and the division. Then it will also have the control flow instruction execution, such as jump and conditional branches. Then the specialized operations called as the capabilities on the SIMD operations for multimedia processing. So these are some of the supported operations of an instruction set architecture. That is, you can say these are the characteristics of an instruction set architecture. So this figure just shows an accumulator interacts with the memory for a typical add instruction. So let us say so the instruction will be executed from the memory. So it will be decoded. So once it is decoded in the sense what operation is performed. In this case, it's an addition operation. So the decoder identifies that instruction is an addition instruction, then it is decoded. Then like the function of the program counter here is the program counter holds the address of the next instruction to be executed. So the address will be taken and it will be executed by the ALU, and the results will be stored in the accumulator. So this figure shows an example of how an accumulator interacts with the memory, and it executes the add instruction. So the instruction will be executed in the steps, that is fetch, decode, and execution. So already we have seen the different types of the addressing modes, that is immediate addressing mode, direct addressing mode, indirect, and register address. So like we have seen immediate and direct. In the indirect addressing mode, the data will be mentioned in a register or the uh, memory. So in the register addressing mode, the data will be data will be mentioned in the registers, like the general purpose registers and the special purpose registers. So these are some of the addressing. So we'll see some an example of some of these addressing modes. Let us say in the immediate addressing mode, as I've said, in the immediate addressing mode, the immediate data will be mentioned. Let us say like 10H is an hexadecimal number. Let us say add 5 is an instruction. So in the register here, so add 5 is a immediate value here. So then in the direct addressing mode, the address will be mentioned. That is that the load memory 1000, so and the register B. So this is about the direct addressing mode. That is, here the memory address 1000 is specified in the instruction. The processor retrieves the value stored at that address and loads the value into the B register. Then in the indirect addressing mode, the instruction provides the memory address, like 200 is the memory address here. The processor fetches the value stored in this location. That is the value stored in the address 200 will be fetched, and it will be stored in the it will be stored in this it will be stored in the um, R2 register. So in the, like when we are writing an assembly language program, we use like which kind of data we are mentioning. So in the indirect addressing mode, so will be the value present in some particular address will be stored into the registers. So these are some of the examples you have seen about like how the data is mentioned in the immediate addressing mode, direct and indirect. So the importance sizes, as you have seen already, the efficiency, if you use more like more bit sizes and all, the efficiency, data range, and the instruction compatibility of these things are measured. Yeah, we have seen these like 8-bit instruction set architectures. So there's a comparison here. 8-bit instruction set architecture that is often found in the microcontrollers and processors like 8086, 8051 microcontroller and other things. So the example of 8-bit ISA, that is instruction set architecture, is the Intel 8088. Then the 16-bit instruction set architectures are more efficient as compared to the 8-bit one. The examples of these are Intel 8086 microprocessor, and this is an the image of the same. So in this, it is having the features like graphical user interface and all compared with the 8-bit ISA. Then in the 13-bit instruction set architecture, processors are more powerful than the 6-bit one. It is having wide spread of the personal computers for several decades now, and provides a significant boost in the performance in the memory addressing capability. So the example of this one are 80886 of 32-bit. Then the 64-bit instruction set architectures are more faster compared to the 8, 16, and 32-bit. The current domain architecture for personal computers and high performance computing, and it enables the processing of large data sets and complex calculations. So the example of 64-bit instruction set architecture is the 8086 of the ARM processor AMD of 64-bit. So these are some of the types of the processor sizes. Let us say when we say 64-bit processor means it will at one time the instruction size of that each register will be 64 bits, so that the speed of operation will be very high. Then we'll see the instruction the instruction operation or the types of instructions supported to the instruction set architectures are these are like arithmetic instructions, logical instructions, data transfer and control flow operations. So we'll see these one by one. So we'll see now the different types of arithmetic instructions available. So the first one, the first type of instructions available are the arithmetic operations instructions. That is, it is responsible for performing and arithmetic instructions like addition, subtraction, multiplication, and division. Then there are logical instructions available. That is and, or, not, nor. Then the data transfer instructions between the memory and IO devices. Then the control flow instructions like flow like the decision loops or function calls or the decision loops. So instruction operations in instructions operations again, arithmetic operations, that is arithmetic instructions, we have different types again here. That is addition. So this addition is represented with ADD. It will perform the addition operation, which are used for calculations, summing numerical values, calculating or finding averages. Then the subtraction operation will do the subtraction operation, which are used in repeating addition or scaling data or applying filters to the images or multiplying coordination for the 3D graphics. Then the division operations will do the division operations, which are used in splitting quantities proportionally, that is calculating rates. So the example of these division are calculating the shares in the profit, then dividing sources among the tasks. So these are different types of operations and their applications. That is, let us say, like logical operation. The logical operation and performs the checking if multiple conditions are true or not simultaneously. So this and operation thing is used in the authentication with the username and the password. So these are some of the instruction like operations which are used in their application. Let us say like OR operation. So the OR operation will do the checking of at least one condition is true or not. So the application of this OR operation is will be in checking if a key is pressed or not, like in that case. So these are some of the examples of that one. Then the NOT operation used for inverting a bit value. If you want to change the value from 0 to 1 and 1 to 1, so in that case we'll use. So the example of is not gate are the toggling switches in a user interface, or reversing signal directions in the circuit. Then the XOR operation, all of you know the tutorial of the XOR operation, which are used for finding the difference between the two bits, whether the two bits are same or not. So these XOR gate operations are used in the applications of error detection in data transmission. So these are some of the logical operations which are used, and their real-time applications available. Then the data transfer operations, all of know that the load and store operations are performed. So this load basically does it is used to move the data from memory into the register for processing. So for example, the application is loading a character from a file into the memory for display. Then the store operation will move the data from the register into the memory storage. The example of this one is storing the results of calculation back into the memory. So these are some of the arithmetic operations and their real-time applications which are used. Then the control flow operations, operations like jump instructions, they are unconditionally jump from one place to the another place in a program execution, and the jumping to a new section of the code after completing the task is the importance of this jump instruction. Then the branch instructions, like it is mentioned with BEQ and BNE, so which use a conditional transfer program execution based on the comparison. For example, branching of an error handling routine if an input variable is invalid. Then there is a call operation also, which is mentioned as CALL, so which is used to invoke the subroutine or a function, allowing the modular code. So the example of application of call is calling a function to sort a list of elements, that is ascending or descending. Then the return operation, as the name itself, it is used to return from a subroutine function. The examples will be returning the storage list in the function called previously. That's it in the today's presentation. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.